are working through section 7.4, integration of rational functions. I'll do a quick overlap, and then we're going to jump right into using the method that we showed you last time, called the cover-up method, and that's kind of what I'm going to focus today on. And we will get that finished, I'm pretty sure. And then we can start at the beginnings anyway, maybe even get a question done on the general algebraic method. Let's start. You're going to end up integrating guys that look like this, so let's make sure that we know how to do those. If it's just an x plus or minus a number, it's a natural log of x add 2. In this case, it's 3 times the natural log of x minus 7, with or without the absolute values. In this one, the answer is not just that guy. It's not 4 times the log of 2x minus 3. What else is it? What have I missed? That 2x does something, in particular that 2. If you wanted to prove it, you could do a U sub, but there's a quicker way to figure out what the effect is.
It
What does that?
changes 1/2.
Yeah. So you divide by 2, you get a half. So in fact, the correct answer to this one is 2 natural log of 2x minus 3. It's a common mistake that when you do one of these integrals that you forget the multiple of the x's, you don't account for it. If that was 5, we would have a 5 here, right? If that was 20, we'd have a 20 here. So when we do this one, it's not just -3 the log of 4x plus 1, but that 4 gets you that. Are you comfortable with that now? That you got to take account of the 2x or the 4x, whatever might be in your thing. Okay, so let's do some questions. In the homework, 3 to 9 are all the cover-up method. So I'm going to pick some examples of different versions of that. Start off with a very basic one, a nice straightforward one. And so how about question 4? So we have y over y plus 5 and 2y take away 1 dy. So that's the guy we're going to integrate. So the way that we're going to set this up is break it into its partial fractions and then integrate those. So we know it's going to be y plus 5 and a 2y minus 1. Are we happy about how the fraction can be split into 2 baby fractions called partial fractions? And now we are going to find those 2 guys. So here we are. Okay, let's go for this number here, right? The A. We cover this up. You got this number up here. Y plus 5. You cover up the y plus 5. And what number? What do we replace the y's by? What number? You get it from here. What value of y do we use?
-5.
Agreed. So -5 on the top. And 2 lots of -5 take away 1 is -11 on the bottom. So what we get here is 5/11ths. It's okay to have ugly fractions. Just leave it alone. Right, let's get the second one. This one. You cover up 2y minus 1. What's the value of y we use this time?
Positive 1/2.
Okay, so what you get is a half on the top. And a half plus 5 is 5.5, which actually is 11 halves. And if you take a fraction, divide it by another fraction, you turn one upside down, and eventually, can you trust me that you get 1/11th? And we have now completed the cover-up method, right? Now, each of these 2 guys, although they have ugly values at the top, we'll live with that, can be integrated. This fella here is 5/11ths, the natural log of y plus 5. this fella isn't just 1/11. Agreed? Doesn't that 2 contribute to the answer? And won't that basically be, you know, multiply by half or divide by 2, however you want to say it? Are you happy where that 22 came from then? It used to be 11, but you double it to 22. And you're finished. You've now integrated your first question using the cover-up method. Are we good with that?
I have a quick question.
Yes.
So it kind of makes sense if you think about pulling the 5/11ths out first before you do the integral, but why exactly would you not distribute that 11 to the denominator and have it be like 11y plus 55?
Oh, that's an interesting thought. It ends up being the same thing, you know, although it doesn't look like it. So if I've got you correctly, you're thinking, why didn't I do something like this? At least I think this is what you were saying.
Yeah, that's what I was meaning.
Right. Now, according to the scheme of things, the answer should be 1/22, the natural log of 22y take away 11. Now you're going to say, well, the 122 is the same, but this is not. Agreed? And you might think, oh, what's going on? Well, isn't this 11 times 2y take away 1? But not plus c's there, right? So far, so good. Isn't this 1/22, the natural log of 11, plus the natural log of 2y minus 1, plus c? This becomes this guy. Now, this is a number, and this is a number that we don't know. So those two can be combined. And since you don't know what it is, you might as well just call it plus c again. So you see, you end up with the same guy.
Oh, wow. Okay, thank you. That's exactly what I needed to see.
Yeah. And would you also agree it's a lot of work just to get back to where you came from? So we tend to not go this pathway. Okay, let's show you one with a couple of issues. And this is a version of question 5. And it's going to be y. Whoops, I just did that one, didn't I? Yes, I did. Let me take that back. I'm reading the wrong question. This is the integral from 0 to 1, 2 over 2x squared plus thingy plus 1, right? And if you want to integrate this fella, there's a step that is necessary, which is basically, don't you have to make sure that before you start, everything's factored? So can you see in this question, one of the few times we needed to, didn't we have to factor the bottom expression? Right. Now we're ready to go. I won't do this all the way at the end. And we'll split it into a over 2x plus 1 and b over x add 1. Well, let's see what we get. Let's do this 2x plus 1. If I cover this guy up, the number I will use is -1/2. So on the top it's 2, and -1/2 add 1 is +1/2. So this guy here does become something reasonable. It becomes 4. Now if we do the x plus 1, I'll cover that up and replace what, -1 for x. So 2 over -2 add 1, 2 over -1, and that becomes -2 over x add 1. And then, going to move over here, 4 times the natural log of 2x plus 1, and I've made a deliberate mistake, take away 2 over the natural log of x plus 1, evaluated at x equals 0 to x equals 1. What's wrong with the 4 natural log of 2x plus 1? What's missing?
Multiplied by a half or divided
Right.
by
2 multiplied by half is fine. So shouldn't it have been 2? Good. Can we just dot that, because you can finish it yourself. Now, you are going to get questions where you plug in the x 0 or 1 or 2, whatever it is, and you might get an example. Let's suppose we had a question that looked like this, and it was going to be x equals 1 to, well, let's make it something negative, -4 to 1, right? Now you plug in 1, you get 1 add 3, which is okay. And then you plug in -4 and you get that guy. Have you noticed that sometimes they tell you the answer with an absolute value, and sometimes we do it without the absolute value? Have you noticed we have that issue? The only time where the absolute value is necessary would be in a question where, when you're about to put the value in, the number inside the log becomes negative. In that case, isn't it helpful to realize that what you're really calculating is the numerical value, in other words, the absolute value? So you would treat that as the log of 1. If it was -7, you treat it as a log of 7. So just in case you come across that situation, logs of negative numbers are not allowed, so you take the log of absolute value of negative numbers when that happens. How about this question? It's got 2 unusual features of which we haven't really dealt with yet. There's the first one. That's an A. It might look like a 9, but my A's tend to look like 9s. That's an A, the letter A. And somehow or other, we're still going to get the answer. So it's going to be A over x plus B over x minus A. I'll try and make it more like an A. I'm not going to change my process just because I don't quite know what that guy is. So let's get this fella. The number or the term that goes above the x. Right. I'll cover up the x. Now, here's your little puzzle or problem. What value is x going to be now? What do I replace the x with? You know, when it was x minus 1, I used 1. When it was 2x plus 5, I used -5/2, right? What would I use when it's x?
0.
0. Agreed? 0. So what do you get? You get 1 over -a, which is what? -1 over a. And that's the answer. Let's do the other side. X minus a. Okay. I'll cover up the x minus a then. What value of x do I use now?
A.
And 1 over a is 1 over a. Hey, we're almost done. Right, if you integrate this guy, you get -1 over a, the natural log of x. And this guy gives you 1 over a, the natural log of x minus a, add c. And WebAssign will probably take that. And if it doesn't, it will definitely take it if you stick an absolute value around the x and the x minus a. But I want to do style points. I want to make this as pretty as possible. Don't worry about the plus c, that's just going to be there all the time. Is there anything you can see that you might want to do to these 2 terms? Anything that might make it look prettier?
Factor out 1 over a.
Agreed. Now, I'm going to rearrange the order because I don't like negative pluses. They just look weird in my brain, and it's also going to help. Would you agree that we've now got that? So this is that. So far, so good. Now, is there a way to combine those two logs into just one log?
You would divide the terms, so it's x minus a over x.
And you don't really need those brackets. I don't know if you agree with me or not, but isn't this a little bit prettier looking than that? Are we good? Okay, let's move on. We're pretty much coming to the end, except for this guy, number 9. Whoa, big, right? You notice it's got 3 terms on the bottom rather than 2. Great, 3 different terms. So when we split it, it's going to be an a over y, a b over y add 2, and a c over y take away 3. Are you comfortable about how you split that fraction into 3 partial fractions? Does that seem reasonable? We're just extending the idea a little bit. I'll move it over here because I'm pretty sure I need more room. I've got this guy. I'm then going to get a number for that guy. I'm going to get a number for that guy. And we're pretty close to being finished with the method. Whoa. Okay, I'll cover up those 2 and let's focus on just the first term. There's a y on the bottom, so I cover the y up. Don't you replace everything that's left with 0, right? Don't you replace all the y's with 0, which means that the top is -12 and the bottom is -6. So you get 2 over y. Are we happy about the first one then? 2 over y. Middle one, cover it up. Would you agree that we plug -2 in now? Oh, yeah. Oh, at least they cancel. -2 is 4. You get 16 on the top. And -2 times -5, you get plus 10 on the bottom. So if you divide that by 5, you get 8/5 y add 2. Are we happy about that as the second term? So you cover this one up and replace everything that's left, replace all the y's with -2's, and you get 16 over 10, which becomes 8/5. Right, last one. Cover this guy up. Would you agree y equals 3 is the number? Okay, you got to watch me because this is doing it in my head and I'm not great. That's 9/36. Take away 18, so it's 18. I get 6 on the top. And 3 times 5, 3 times 3, 5, 15 on the bottom. And that divides by 3. So I get 2/5 y take away 3. As far as you can tell, did I do that correctly? Got a nod, so I'm going for it. Right, next stage is integrate the first guy, integrate the second guy, and integrate the third guy. And evaluate them at 1 and at 2. So let's see what we get. 2 natural log of 2 plus 8/5 natural log of 4 plus 2/5. If you plug 2 in here, won't you get -1? And I forgot to put my log in there. Won't you get 2/5 the natural log of -1? And what do we do with logs that have negative numbers in them? Don't we just make them positive numbers? So that becomes 2 log 1. Can you see that's one of the few times where the absolute value is probably necessary? So, yes, I know it is -1, but we take the absolute value and we get that. So take away 2 log 1 plus 8/5 log 3. And when you plug 1 in here, you get -2. So that's going to be plus 2/5 natural log of 2. Whoa, that was tight. Okay. Aren't those two guys both zeros? Because the log of 1 is 0. So what have I got? I now have 2 log 2s plus an 8/5 log 4 plus an, not plus, take away I should say, 8/5 log of 3, take away 2/5 log of 2. So far so good? We need style points. We need to make this answer as simple as possible. Is there anything that you can see here that we can do to make that happen? Is there any terms that can be combined, for instance? Does that help? You agree the log 2s? So you've 2 log 2s and you're going to take away 2/5 of a log 2. Well, that's 10/5 take away 2. So you now get 8/5 log 2 plus 8/5 log 4. Take away 8/5 log 3. Does anybody see anything that you can do here to make it look pretty?
You can
Take out
combine them
the-
all to be the 2 times 4 inside of it. So it's 8/5 log of 2 times 4 on the top and then divided by 3 on the bottom.
Agreed. So I'm just going to do what you said, but I'm going to do it in 2 steps. So you're quite right what you said. So couldn't we pull out an 8/5, which might have been what one of the others was going to say. So far, so good. Now, what can you do? Well, can't you take a log, add a log, take away? And that becomes 2 times 4 divided by 3. And that becomes 8/5 the log of 8/3. Would you agree that's much nicer than it started off? And we are always going to think, can I make it look pretty, right? Style points also works when you're dealing with numerical answers. The simpler you can make that answer, the more likely, if everybody follows the same rules, the more likely that we're all going to end up at the same space. And if you don't, and you just leave things floating like that, and then somebody else decides to do this, and then someone else decides to do that, aren't you going to have the problem of 4 different versions of the right answer? And everybody's trying to figure out, is my answer the same as theirs? Second, isn't it just more elegant if the answer's pretty? It just makes sense that you should try and do it if you can. And that is us done everything that uses the cover-up method. So we're now going to be beginning, we'll not get it finished, the general algebraic method. And before we do that, I want to show you something that is helpful. What is the antiderivative of 1 over 1 plus x squared? It is a standard integral. It's one of those ones you just memorize.
Tan inverse x.
Nailed it. That I would expect you to know. You've seen it, used it a few times. You should know it. Here's something you don't know, but it's helpful because it's going to happen from time to time. 1 over a squared plus x squared also has an answer, and that answer is 1 over a, the inverse tan of x over a. So if someone says to you, what is that guy? You're going to say, oh, 2 squared. It's going to be 1/2 the inverse tan of x over 2. And if they give you 1 over 100 plus x squared, it's going to be 1/10 inverse tan of x over 10. And what's it going to be when it's 1 over 3 plus x squared? Your turn. What will that one be?
Would it be 1 over 3/2?
Nope. But
1 over the
you're
square
trying?
root?
Yes. I know where I think I know where the 3/2 came. So you weren't miles away. You were thinking half in the 3 in some way, but it's a half power, so it's the square root. And so basically, can't we now integrate 1 over any number plus x squared? Right. So we used to know that, but now we know this. What would be the effect of putting a number like 22 on the bottom? Because you probably will expect numbers to be in the top. How will this help me get that? What do you do? What's the answer?
22 over square root 3 rather than 1 over square root 3.
Yeah, just 22 times whatever the answer would be, as if there was no number. Are we cool on that? Right. Now, the general algebraic method is horrendously long. It'll take you a while to do, and you only get, I think, 2 or 3 examples in the homework. So, when must I use it? Because I would always try, would you agree, it's much quicker to do the cover-up method if you can. But there are going to be some situations where the cover-up method doesn't work. Now, you might use it, but the answer you get is wrong. Analogy. Can you remember doing L'Hopital's rule? And if you did L'Hopital's rule when you shouldn't, don't you get an answer? It's just not the right answer, right? You can apply the cover-up method, or at least attempt to it, in almost any fraction question, as long as it's factored. But it won't work unless the following is true. So here is when you should use the cover-up method. So here's the 2 situations. First situation, you might not have been aware of because it's always harmed. And that is that the numerator, that's the top, must be smaller power than the denominator, which is the bottom. So suppose you were doing an x minus 1, x plus 7. Would you agree that looks really good? And the top was 3x plus 1. The top here is x, isn't the bottom an x squared? That is good to go. You can use the linear cover-up method. On the other hand, You see this guy here? Looks like you should be able to do it. Do you notice that the top power is x squared and the bottom power is x squared? Do you see that, guys? X squared on the top, and if you FOIL that out, x squared on the bottom. That's bad. Do not use the cover-up method. If you did, you'll get an answer. It'll just be wrong, right? Like in using the L'Hopital when it isn't undetermined or indeterminate form. Are you comfortable with that restriction, right? The top guy's got to be smaller power than the bottom guys. And the second term is there must be only single linear terms on the denominator. And that's the bottom. So 3x minus 1, x plus 1, 3x minus 2, that's good. That's bad. You see that the terms in the bottom are linear, right? And there's only one of each. Here's two examples of bad guy. Do you notice that guy's not x, is x squared? Do you see it's not linear anymore? Can't use the cover-up method. Here's the other situation. You see that term there has a square next to it. It's not 3x minus 2 on its own, right? It's not a single linear term. Isn't it a quadratic linear term, right? It's got a square attached to it. That's bad as well. So the cover-up method is really nice and really quick, and you want to use it. And hopefully you'll get to use it. But if the top power is bigger or the same as the bottom, you can't use it. If the bottom power has a square in it, you can't use it. Even if you try to, don't. So let's look at the general algebraic method now. We'll definitely be doing this tomorrow. Give you a heads up on what questions use it. So it's going to be question 12 and 13. Okay, so there's only two of them. So here's my version. Right, do you notice that this one has an x squared plus 1 in it? That's what makes it a bad guy, right? You can't use a linear cover-up method. You can't use the cover-up method. So this is how the algebraic method starts. You break your fraction into its partial fractions. So it begins very similar. So x plus 3 gets an a. Here's a little difference. The x squared plus 1 term isn't just b over x, it's bx plus c. Do you see that? That's a little different. So if there's a quadratic term like x squared plus 4 or x squared plus 9, that kind of thing, the top term is going to be a bx plus c. Okay. So we've got this fella. Try to make sure I give myself enough room here. Now things take a total different turn. We're not going to cover up anything. We're not going to plug what's left into the fraction on the right. Nothing like that's going to happen. What I'm going to do is I'm going to take these two fractions and I'm going to combine them again. I'm going to put them back together as a single fraction. Now, if you remember how to combine fractions is they have to share a common denominator. And these two fractions right now don't. So what I'm going to do is I'm going to multiply this fraction by x squared plus 1. And this, the second fraction, I'm going to multiply it by a special version of 1 called x plus 3. Now, the reason why this works algebraically is, would you agree if you multiply a fraction by 1, you don't change its value, you just change how it looks. And if you multiply it by x plus 3, right, this fraction here, by x plus 3, top and bottom, that's just 1. You don't change its value, you change how it looks. But what you do get is now two fractions that have the same common denominator. So now what I have is ax squared plus 1 plus bx add c x plus 3 all over the same fraction. Are you with me so far? Okay. Now I'm going to take away the integrals and the dx's because they're in the way and they just slow things down. So I'm just going to focus on the fact that this fella here, mathematically, is equivalent to this guy. Now, if two fractions are equal to each other, and those two fractions have the same denominator, does it seem reasonable to make the assumption that the top two terms are also equal? And that means I can now write down 4x add 2 is equal to ax squared plus 1 plus bx add c x add 3. Are you happy with the logic to get to there? Now you might think, oh, where do I go now? And I'm sure the person who created this, whoever he or she might have been, probably had the same thought process. And then a light bulb moment probably happened. And they made this conclusion. In mathematics, if two things are equal and they have x's in them, then aren't they equal for every value of x I can put? So if I put x equals 42 here and x equals 42 here, wouldn't the expression I get still be equal? And so what they figured out, and this is how the method now works, is you choose a value of x. And you don't just randomly pick numbers, because if you do that, you'll be here all day. You are very specific about how you pick your numbers. You pick them in such a way that you destroy or remove, maybe a better word, as many of the variables as you can and only leave one of them behind. So why, for my first choice of x, why am I picking x is -3 to substitute everywhere in here? Why x is -3?
Because it gets rid of the x plus 3.
And won't that disappear as a big fat 0? So 4 lots of -3 add 2 is a times -3 squared add 1 is 10 plus Something times 0 is 0. So I have negative 12 add 2 is 10a. I have negative 10 equals 10a. And now, almost like magic, haven't I found out who a is? Sneaky. Because I now know that a has to always be negative 1, because if it works for this, it has to work for all the other choices. I can now rewrite this top line a little bit differently. It's not a times that, it's negative 1 times that, plus the other stuff. And now we get to choose another x. Have you noticed that we only have two missing things, a b and a c now? A is taken care of. We know a is negative 1. We found what a has to be. Now you might think, oh, wait a minute, if I picked another x, a might be 42 the next time. No. Once a has a value, it must be that value no matter what x's you choose later. Okay, give me a good choice of x to now replace in this expression so that one of the letters disappears on us and I only are left with 1, 1. Give me a value for x that kills off one of those two letters, the b or the c.
Zero.
Would you agree that 0 kills the b? Let's do it. 4 lots of 0 plus 2 is negative 1 times 0 squared add 1 plus b times 0 is just 0 add c and 0 and 0 add 3. And let's make this a little bit prettier. Negative 1 times 1 is just negative 1. Nothing add 2 is 2. C and 3 gets me 3c. Add 1 to both sides. And divide. And guess what? We now know what c is. C is negative 1. And I now go back to that top expression and I replace the c with 1. So now we have 4x add 2 equals negative 1 x squared plus 1 plus bx add 1 instead of bx add c, x add 3. Do you see that every time we do it, don't we get simpler and simpler relationships? Now, in this last version, isn't there only one missing letter and it's b? And we choose an x equals. And you might say, well, who do we choose when there's only one number? The good news is anybody you like, as long as it's not negative 3 and 0, right? As long as you don't choose negative 3 and 0, you're fine. So you might say, can I choose 42? Sure you can, but I'm not going to. Could I choose minus 17 411ths? Yes, and it would work, but I'm not going to. Shouldn't you pick a number that makes your life easy? Right? Because any x will do, they all end up actually getting you the right answer, the same answer. So see if you can think in my brain. What number do you think I'm going to pick because I'm bad at counting?
1.
That is exactly the number I'm going to pick. Would you agree that's a good number to pick if you want to make your life easy? So what do we get? We get 4 lots of 1 add 2. Negative 1, 1 squared plus 1. B times 1 is just b add 1 and 1 add 3. So that's 2. So we'll get negative 2. That's 6. B add 1 times 4 is going to get me 4b add 4. That's going to get me 4 equals 4b. I do not know because to be honest, I just randomly picked that. But I got really, really lucky with the numbers. Would you agree? I could have easily got 7/4 and minus 22, right? There's no particular rhyme or reason why everybody has 1. It does, however, mean that I am very close to being finished, but not finished, just very close to being finished. So the original integral, which was this guy, now becomes a over x plus 3, and a was -1. And then it was add bx add c. So it was add 1x plus c. So it's 1x plus 1 all over x squared plus 1. So there's the a, there's the b, and there's the c. You happy about where we are right now? Now, what you should typically do next is split the integral into 3 pieces. In particular, this guy here has been separated out. So it's an x and it's a 1 on its own. Now this fella here is pretty easy. He's a natural log. What's the integral of 1 over x squared plus 1? Or 1 over 1 plus x squared, if I have to write it that way. Oh, come on. Inverse people amongst you. Come on. What is it?
It's inverse tan, right?
Yes, it's the inverse tan. Now, what do you think I'm going to do to that middle guy? X over x squared plus 1. What method am I going to use to solve x over x squared plus 1?
U sub?
It is. And the u sub is going to be x squared plus 1. And you lot are just going to have to trust me on this, but eventually you get that. In this question here, I don't think there's really much point in trying to do style points. I don't think you're going to get really any great benefit, so I would just leave it.
I have a quick question.
Yes, Dylan.
How did you get 4b? I seem to have missed that.
Okay. What I did is I added these together, so I had a missing line in the middle that looked like that. And then I subtract 2 from both sides, and then I divided by 4.
Okay, I see. Wait. Actually, just how'd you get the 4b part? Because you have b up there, it's b
I
plus
have
1.
a b plus 1 times 4, which when you distribute it gets you 4b plus 4.
Ah, okay, that's it. Thank you.
That's his last name. Bye-bye. I'll hang